Real exam questions. This is question 56 about beam design. Determine the reinforcement, the tension reinforcement and the compression reinforcement with diameters and numbers of bars that just meets the rotation capacity. The reinforcement is in one layer. The bending moment is 1,490 kilonewton meter in ultimate limit state persistence. And the point of gravity, D1 and D2, is 70 millimeters. Concrete quality is 30 megapascal and the steel quality 500 megapascal. So rotation capacity. When we think about that, then we know that there is a limitation on the depth of the neutral axis and that x over d, so c, must be smaller than 0.45 times d. X must be smaller than 0.45 times d. And this is for a concrete quality of less than C50. So we have to limit the depth of the neutral axis. Let's look at the strain diagram. For the concrete, on the right-hand side, the steel on the left-hand side, the beam is 500 millimeters. And the concrete cover or the position of the point of gravity of the tension steel is 70 and of the compression steel is also 70. D is 430 millimeters. And this is the strain diagram where we reach the maximum strain in the concrete of 3.5 per mil. This is the strain in the compression reinforcement. Notice that the epsilon S2 is very close or relatively close to the 3.5 per mil. So it means that this is probably bigger than 2.17, but we have to check it that this steel is also yielding. This is the tension in the strain in the tension reinforcement. It's somewhere between 0 and 10 per mil. And we know, because of the limitation of depth of neutral axis, that C must be smaller than 0.45. So this is the strain diagram with the knowns and unknowns indicated. The general rotation around the tension reinforcements in dimensional units gives you this equation with delta G and C are known in the region 2A. The C value of rotation is 0.45. So when we put in the different numbers, we see that the mu rotation is equal to 0.296. Now, we have to start with a certain value of the strain or of the stress in the compression reinforcement. We know that it's likely that it will yield, so we start with 435 megapascal. We know that the reduced bending moment that we are looking for is 0.296. So the compression reinforcement is the difference between the actual bending moment and the target bending moment divided by the lever arm. So MD we can fill in with the proper units. Mu limit we know it's 0.296, B is 1 meter, D is 430 times FCD, it's 70 megapascal divided by the stress. But remind, this stress, it's a gamble, so we have to check it if this is right. And D minus D2. If you obtain a negative value, that means that you do not need compression reinforcement to obtain mu limit smaller than 1296. Now we have to choose compression reinforcement with this as an absolute minimum. So we choose something easy, 12 diameters 20, which is 3,770. So it must be bigger than this, otherwise we will not obtain rotation capacity. So 12 diameters 20. The nominal bending moment is then the difference between the bending moment that is applied minus the bending moment that is created by the compression reinforcement. We fill in the different parameters and we have 900 kilonewton meter. The reduced bending moment for the nominal bending is then equal to this bending moment that we found, 900 kilonewton meter, divided by the width, the effective depth squared, and FCD. And it gives you 0.2863. Now, from this, we can go to the tables, which is easy, and you will see that for the reduced bending moment between those two, we will look for C and we will look for zeta. Just by linear interpolation, we find C, which is x over d, is 0.43. So this is smaller than 0.45. That's fine. That's what we want to obtain. And zeta is the lever arm to calculate the reinforcement, amount of reinforcement. Interpolation with mu equals to 0.2863. We find that zeta is 0.821. So the nominal tension reinforcement is then equal of the bending moment divided by the lever arm and the yield strength of the reinforcement. It gives you 5,861 square millimeter. Now we will check and, if necessary, iterate this equation that the calculation that we've done on sigma S2. So we first will see if sigma S2 has yielded yes or no. Delta 2 is then D2 over D, 70 over 430 is 0.1628. So we can, from similar triangles, easily calculate the strain in the compression reinforcement, starting with the strain in the concrete. It's just proportional. And then we find that this is 2.18 per mil. So that's fine because this is yielding. So it means that the stress in the compression reinforcement is 435 megapascal. If not, if this was, for instance, smaller than 2.17, then you redo the calculations with another value of sigma S2. So sigma S2 is then, of course, epsilon times modulus of elasticity, 436. So we started with 435. So if the difference is less than 1%, then we stop the iteration. So in this case, it is almost equal. So we have the beam, 1 meter width, 500 millimeter in depth, with the reinforcement. The compression reinforcement is then the tension reinforcement times the ratio of the stresses that we've calculated. So, but we know now 435, 436, it will not give a big difference, but just to give you a complete picture of how to calculate it, I've written it down. So it's 3779 in itself, 3770. That's the complementary reinforcement. So it means that the total tension reinforcement is the nominal reinforcement, 5861, plus the complementary reinforcement, which is needed to achieve our goal of rotation capacity. So it's 9,640 square millimeter. And 9,640, you can obtain it by 12 diameters 32. So to comply with rotation capacity, the reinforcement of the beam is tension reinforcement 12 times diameter 32 and compression reinforcement 12 times diameter 20.